We have here a handout on the topic Big O complexity, which is from the subject CS 106B of Stanford University. It's good for them to freely provide this for use for learners. So we might as well also discuss this one. This is about Big O, and it is to denote the computational complexity of algorithm. When using big O notation, the goal is, again, to provide a qualitative insight as to how changes in n, the input size, affect how many units of computation are performed. This is referring to time complexity performed for large amounts of data. So take note always that big O refers to the worst case behavior of an algorithm in terms of its running time when the input size becomes very large. First, for computing the big O, from the time function, say this is our time function here, n squared plus n. Always remember that our basis for getting the big O is the time function, which is the frequency count of the computations performed in the algorithm or the program. So if that is the time function or the approximate runtime function, n squared plus n, then we have here two terms, right? N squared and n. And we only look at the term with the highest power, or the term that grows fastest when n becomes very large. So of these two terms, it is n squared that grows very large compared to n. And that is why we simply say that the big O is O of n squared. And in the case when the term has a coefficient, we simply cancel that one out. So instead of O of 3n, say for example, Tn is equal to 3n, then the big O is simply O of n. We cancel this out, the coefficient. Because to compute big O, if we think about the number of executions referred as the frequency count of the code will be performed in the worst case scenario. The strategy for computing big O depends on whether or not your program is recursive or iterative. For the case of iterative solutions, we try and count the number of executions that are performed. For the case of recursive solutions, we try to compute the number of recursive calls that are performed. Again, as mentioned before in our previous slide, for the case of iterative code, like what we have here, it is iterative code because we are making use here of a for loop. So let's find out the complexity, the big O of each code. So the first one is one for loop only, and the number of iterations, as you can see here, your x is set initially to n, and while x is greater or equal to 0, we decrement x. The value of x would proceed from n, then n minus 1, n minus 2, up to 0. So from n up to 0. 0 is included because of that equal sign, greater or equal. So how many iterations are this? It will be n plus 1, right? That is n, and we have here zeros, so there will be n plus 1 iterations. So this body of the for loop is executed n plus 1 times. And so the number of execution of the operation is n plus 1. And if we get the big O, that will simply be O of n. Okay, because we have here two terms. This is constant one, while this is the term that will grow fastest when n is increased or when n becomes very large. Now here we have nested for loop, outer for loop, inner for loop. And notice that in our previous examples, when there is only one for loop, the big O is linear. And if we have nested loops, like in this case, outer for loop and inner for loop, then this is what? If this is n, or any variable which represents the input size, this would be quadratic. But notice that the number of iteration is fixed. It is not dependent on some variable like n. The outer for loop is from 0 up to 4. 5 is not included. While the inner for loop, j is from 0 to 9. 10 is not included, okay, because it says here j less than 10. So it is only until 9. And so this operation, which is to display the value of j, is executed how many times? 0 to 4 is 5 iterations, and j is 0 to 9, so that's 10 iterations. So 5 times 10, that is 50 times you execute this 50 times. Now take note that every time you run this code, this will always be executed 50 times. So that is constant. So the big O is O of 1. Neither loop depends on the value n or the input size n. It is constant. On the third example, we have here nested for loop again, the outer for loop and the inner for loop. But this time, the number of iterations is dependent on variable n, where n, say for example, is an input value. Your I would proceed from 0 up to n minus 1, n is not included, and your j for the inner for loop would proceed from 0 up to n minus 1 also, n is not included. So how many iterations are there for the outer for loop from 0 to n minus 1? That is simply n iterations, right? For the inner for loop, j from 0 to n minus 1, that is again n iterations. So for every value of this, there will be n iterations. So the number of times this operation is executed is n times n, or simply n square. Okay, that is why the big O is O of n square. The outer loop executes n times, and each iteration, the inner loop executes n times, totaling in n square iterations. So we call this again the quadratic complexity. This one as the constant complexity, and this is the linear complexity. The fourth is a single for loop, and this operation here to display hello is executed how many times? Your I, loop variable I, is from 0 up to 5n minus 1, right? 5n is not included. And so, from 0 to that, that would be 5n iterations. So this statement here, in the loop body, is executed 5n times. And the big O of this frequency count is simply O of n. We eliminate the constant. The fifth iterative code we have here is a nested for loop. We have here the outer for loop and the inner for loop. The number of iterations for the outer for loop would be your loop variable I is from 0 up to n minus 1. N is not included because it says here I less than n. And for the inner for loop, the loop variable j is from 0 until that is simply n square minus 1. So that value n square minus 1, because the value of j is not to become equal to n times n. So it's 1 less than this because it says less than. There is no equality operator. So it's just less than. So this would be n squared minus 1. So how many iterations would this be? For the outer for loop, it is n, while for the inner for loop, it is n square iterations. So for each iteration of this from 1 to n, iteration of the outer for loop, this inner for loop is executed n square times. So the approximate time complexity would be n times n square. And so the big O is O of n cubed. This is cubic complexity. Now recall this expression we have in the previous video when we let complexity of n to be that the sum of 1 to n, that is simply denoted as I from 1 to n, or big N. So that is simply 1 plus 2 plus 3 plus up to n minus 1 and plus n. And remember that this is simply equal to n times n plus 1 over 2, and we already proved this to be equal in mathematics. This one is equal to this one. Now, if we're going to separate this, if we are going to perform algebraic manipulation on this expression, meaning we want to separate this into two terms, then that is simply n squared plus n over 2, right? Which is simply 1/2 n squared, this one, plus this one, 1/2 of n. So this is our first term and the second term. And which of these two terms would grow the fastest when n grows? It would of course be this one, right? It's 1/2 n squared. We can eliminate this constant or the coefficient, so that would simply be O of n squared, quadratic complexity. Now we have here another problem, and that is the problem of dividing in half. And this is called binary search. It works by dividing a search space of number in half until the algorithm finds the target value. In the worst case scenario, it must repeat this process until the search space only has one element. So the question is, how many times can you divide n in half until you have only one element? So mathematically, we represent that by this expression, how many times you divide n by 2, such that the result will be only one element in each group or division. From mathematics, x is simply log of n base 2, right? So that is equivalent to saying 2 to the x is equal to n. And thus, the big O of binary search is O of log n. Okay? Where x is the number of times we can divide n by 2, so that the final grouping will consist only of one element per group. The next problem we are going to tackle is the problem on recursive algorithm. If we're going to compute for the big O of a recursive function, it will be of the form where you simply need to calculate the number of calls in the recursion call tree. Often the number of calls is big O of b to the d, where b is the branching factor, worst case number of recursive calls for one execution of the function, and d is the depth of the tree, the longest path from the top of the tree to a base case. And the depth is n, where n is the number on which the function is called. Say, for example, this given Fibonacci function here, if we call this as Fib5, Fibonacci 5, then our n is 5. Okay? So 5 is the depth, right? So d is the depth of the tree, which is the longest path from the top of the tree to a base case. And this depth is also the number on which the function is called. This function is called on this number 5. So this is the depth of the tree. Look at this function. We have here two cases. The base case is this one, or we also call this the stopping case. And this part here is the recursive case. Okay? Because as we have discussed in our programming subject last year, a recursive function will always have two cases, the stopping case, or also called as the base case, okay, this one, the base case, and the second is the recursive case. The recursive case contains recursive calls. Recursive calls meaning you call the function again. So what makes this function a recursive function? Because of the recursive calls, which in this case there are two, right? And so b is equal to 2. O of b to the d. Okay, this is the big O of recursive codes or recursive functions, where b is the number of recursive calls. Like in this case, 1, 2. In this one return statement, there are two recursive calls. So b in this case is equal to 2. And d is the depth of the tree. And it is also the number on which the function is originally called. So if this is the original call, fib5, what is the depth of the recursive call? So the original is fib5. This would give you fib4 plus fib5 minus 2 is 3, right? And then fib4 is fib3 plus fib2. And then fib3 is fib2 plus fib1. And fib2 is fib1 plus fib0. So the root original call is fib5, and then it branches into 2. You have this and this. So you have fib4 first call and then the next call. And then this one is fib3 and this is fib2, right? And then fib3 is fib2 and fib1. And then fib3 is also fib2, fib1. And fib2 is fib1, fib0. Fib2 is also fib1, fib0. And this is also fib1, fib0. So what is the depth? It is 5, right? 1, 2, 3, 4, 5 levels in the recursive tree. The depth of the tree is 5. From the original recursive call up to the base. Okay, the base or stopping case is when n is less than or equal to 1. Okay, so fib1 is base case, base case. This is base case. All of these are base case. And the levels, the number of levels in the tree is 1, 2, 3, 4, and 5. So D is 5, B is the branching factor, branching out. So for every node in the tree or for every recursive call, that would result to 2 calls. And this call would result to 2 calls. This would result to 2 calls. This would result to 2 calls. This one, 2 calls. This one, 2 calls. This one is 2 calls. And this one is the base. And this one, 2 calls. So the big O for any recursive function or code is O of B to the D. So in this case, if our call is fib5, what is the big O notation? It is O of 2 to the 5. right? That is the big O of fib5. So here it is, the tree that we construct when we call fib5. So it calls fib4, fib3, fib4 calls fib3, fib2, fib3 calls fib2 and fib1, fib3 calls fib2 and fib1, fib2 calls fib1 and fib0, fib2 calls fib1 and 0, fib2 calls fib1 and 0. So all these are base case. They are not recursive calls anymore. And so, as we have discussed a while ago, this is depth 5, 1, 2, 3, 4, 5, which is that value. So that's the depth. And the branching factor is 2. For every recursive call, it results to another 2 recursive calls. So with this formula for the big O of recursive function or code, we then say that for fib5, the big O is O of 2 to the 5.